This program is brought to you by Stanford University. Please visit us at stanford.edu.
Michael.
Yeah, the same explanation you just gave.
Yeah.
Supposing in the framework of QFT, and we have a singlet with space-like separation of the parts of the calculation, I suppose you'd say. Is there some sort of virtual exchange of something?
When what happens? Under what circumstance?
Well, let's say under the circumstance that something is measured on one side.
I wouldn't say so. I would say nothing happens at the other side. Nothing detectable happens at the other side until a message can get there. The degree of entanglement remains. Whatever you do at the other end, you may change things at the other end, one way or another, but that electron which is over there will stay entangled with the system over here. It'll stay entangled even though the system may change. It'll still stay entangled. Maybe we can work out an example. Maybe at some point I'll work out exactly the example. Supposing you rotated the spin on the right hand by putting it in a magnetic field, how does the state vector change for the two-particle system, and is there some sense in which the measure of entanglement remains the same? And the answer is yes, there is. We haven't talked about measures of entanglement, quantitative, how much entanglement is between systems. But as long as those systems don't start talking to each other again, there's a measure of entanglement which never changes between them, even though the particular form of it can change. Somebody asked me about what happens if you can take an entangled pair and you throw one of the particles into a black hole. What happens to the entanglement? Well, it becomes entangled with the degrees of freedom of the black hole. The black hole evaporates. That electron over there is still entangled with all of the photons that come out of the black hole and so forth. And in fact, I mean, you can think of much simpler examples in black holes, or much where the whole story sounds very crazy, but nevertheless, forget black hole. Just take a bathtub. A bathtub, you have a pair of electrons. They're entangled in the singlet state, and the bathtub is full of water. And you take, forget electron or atom, could be a water atom. Are there water atoms? Yeah, okay. Two entangled water molecules, and you drop one of them into the bathtub, and it gets all mixed up, terribly mixed up with all of the stuff in the bathtub here. This electron is still entangled, not so much with the single electron which is there, but in the entire state of the bathtub. You have to now treat the bathtub as a system and talk about the entanglement of the bathtub with the electron here. This electron gets too mixed up with the others to have a clear identity, but nevertheless, the state of the entire bathtub here stays entangled with the electron, and then the bathtub can evaporate so that there's no molecules left. There's nothing left to be entangled with. Well, of course there is. What's left to be entangled with is all of the vapor that escapes out of the bathtub. And that entanglement will remain there, frozen in, unless something from this side actually comes over to this side and they interact with each other again. Then they can become disentangled. It is quite possible to take an entangled state and disentangle it. Anything that can go one way can go the other way. So if you were to take two unentangled electrons, let them interact for a while, they become entangled. Anything that can happen in the opposite direction. So disentanglement can take place, but only if the systems are close enough to actually interact with each other. So if something from over here comes over to here, it can get disentangled, but only then, yeah.
In the experiments we've been talking about, where let's say you have entangled electrons and you're going to measure on the z-axis or up and one down. When you make both of those measurements, are they still entangled, those two electrons? Or does the measurements kick them out?
No, the measurements kick them out.
Okay.
Yeah.
And would one measurement disentangle them?
It can. we're gonna talk about that. Those measurements are called measurements. They're called observations, and we're going to talk tonight about how observations or measurements have the interplay between the measurement concept, the collapse of the wave packet, and the concept of entanglement. I want to get to that, but before I do, I want to just spend a little bit of time, because I don't think I did it very well, talking about projection operators and a little just review a little bit of the mathematics. Just very briefly discuss subspaces and the mathematics of subspaces and projection operators, at a very elementary level. I don't like to do anything more advanced, to use more heavy hammers than are necessary to explain an idea. All right, first of all, when you have a space of the kind that we're talking about, where you have a concept of vectors and their complex conjugates, they're formally called dual. The bra vectors and the ket vectors are called duals of each other. We're inclined to sort of think of them as like complex conjugates. We have a concept of orthogonality between those vectors. As long as we stay in vector spaces which have finitely many dimensions. Incidentally, first of all, what's the question? What's the definition of the dimension of a vector space? The definition of the dimension of a vector space, we ought to give it abstractly. Forget for the moment using column vectors and just counting the number of entries. Give you a collection of abstract vectors with some orthogonality relations, and in particular some relations of linear dependence. Linear dependence means that a vector may be linearly dependent on some other vectors. That would mean that the first vector can be expanded in terms of the other vectors. That's what linear dependence means, that you can write a particular vector in terms of another subset of vectors, then it's said to be linearly dependent on it. The dimension of a vector space is very simple. It's the maximum number of linearly independent vectors that you can find in the space. In other words, in three-dimensional space, you can find, there are many, many triplets of vectors which are linearly independent. Linearly independent means that you cannot write any one of them as a sum of the other n minus one of them. Or an equivalent way to say it is that you can't find any linear combination of the vectors which adds up to 0. If you can't, then those vectors are said to be linearly independent. Now, obviously, there's no way that these vectors are not all in the blackboard, incidentally. This one's sticking out of the blackboard. Those three vectors are not linearly dependent. They are linearly independent because there's no linear combination of them that adds up to 0. Another way to say it is there's no way to expand this third one in terms of these other two. They don't have to be orthogonal to be linearly independent. If I take three vectors, I'm not very good at drawing these things, but take three vectors which happen not to be orthogonal to each other, just those two, plus this one over here where this one is not lying in the plane of the other two, there is no way to write the third one in terms of the other two. So again, they're linearly independent. All right. Now, on a three-dimensional, let's start with a two-dimensional vector space. What's the maximum number of linearly independent vectors I can find? The answer is 2. If I add a third one in the plane, if I add any third one, and now I'll just draw exactly the same thing, but think of it now as a vector in the plane, then this third one can be written in terms of the first two. For example, we can add these two and get a vector over here. And then with a minus sign, we're allowed to have minus signs. We're allowed to multiply by constants. We're allowed to add vectors, multiply them by constants. We can certainly build this vector from the other two. So these three vectors that I've drawn on the blackboard are not linearly independent. They're linearly dependent. The maximum number of linearly independent vectors in a two-dimensional space is 2. The maximal number in a three-dimensional space is 3, and so forth. And that's the basic definition of the dimension of a vector space, the maximum number of linearly independent vectors. Now, it's a theorem which we're not going to prove, but it's straightforward to prove that if you can, in a d-dimensional vector space with a concept of orthogonality in it, that you can always find d basis vectors. D basis vectors, the basis vectors mean that the vectors are first of all normalized. That means they're unit vectors, and they're all orthogonal to each other. You can find d of them. So in a two-dimensional space, and in many ways, not just in one way, in many ways, but in particular, there exist families of vectors which are orthogonal, mutually orthogonal, and unit vectors. 2 of them in a two-dimensional space, 3 of them in a three-dimensional space, and so forth. And those vectors, or a set of such vectors, yes?
If you have a 3-point particle, does it have the same number of...
If we have a three what kind of
A
point?
3-point particle.
Three particles.
A 3 particle that is a point particle. Does it have the same number of degrees of freedom as the number of space dimensions?
You're talking about particles moving in space now.
Yeah, a single particle.
Well, that's a definition. The number of degrees of freedom is, yeah, you would say it has the number of degrees of freedom as, but that's not got anything to do with the dimensionality of the space of states.
Right.
Nothing whatever. I mean,
just for spatial dimensions.
yeah, just the spatial dimensions, right. But the dimensions of the space of states can be very, very much larger than the dimension. Take a particle moving in a room. There are 3 dimensions for it to move in, but there's a huge, huge number of possible states of the particle, orthogonal states, so they're not connected in any simple way. Okay, now, I think I lost this. All right, so you can always find a mutually orthogonal set of unit vectors. They're called basis vectors. They're not unique, but once you find the basis, you have a basis. And so let's imagine then that we have a set of basis vectors. We'll call them n, where n is a numerical integer that can run from 1 to the dimension of the space. We have d such vectors, and they're orthogonal to each other, mutually orthogonal. So that means that m and n give 0 unless m is equal to n, in which case it gives 1. So the symbol for that is the Kronecker delta symbol, and the Kronecker delta symbol simply means the right-hand side is 1 if m is equal to n, and it's 0 if m is not equal to n. All right, so that's basically the definition of a basis set, or a set of basis vectors for a space of the kind we're talking about. Now, here's an interesting theorem, which is hardly a theorem, it's more or less obvious, that if you have a basis set which has as many vectors as there are dimensions in the space, then it follows that any vector whatever can be expanded as a sum of the basis vectors with coefficients, with a set of coefficients. Let's call those coefficients a sub n times n, summed on n. In other words, this is just saying that any vector anywheres can be expanded in terms of, in 3 dimensions, the 3 basis vectors or whatever. All right. And now we can relate the expansion coefficients here to the inner products of these psi's with the basis vectors. Let's do that. Just take the inner product of this equation with any vector on the left, with any one of the basis vectors on the left. And so we find that m psi is equal to sum on n, a sub n, m n. Now this is a sum on n, but there's only one term, because only when n is equal to m do we get an answer, do we get something non-zero. When n is not equal to m, they're orthogonal. When n is equal to m, then you get the answer number 1, just 1. And so you get only one term in here, and that term is just equal to am. All right, it's summed on n, but we sort of picked out, we've selected out m to project onto psi, and the whole answer then is just am. All right, so that's a nice simple fact that the expansion coefficients here for a given vector are nothing but the inner products of the psi vector with the basis vectors. That tells us what the a's are. If we take the, now I can rewrite the equation. Let's rewrite this equation. We now know what the a's are. Let's write it in the following form. Psi is equal to sum on n. And now instead of writing a, I'm going to write this inner product. The inner product is just n psi, that's an, times n. I've taken the liberty of writing the coefficient on the right side of the vector instead of the left side of the vector. That doesn't, you are allowed to write 3 times psi as equal to psi times 3. That doesn't, no objection to that. So this is a number. This is the inner product. This is the nth basis vector. It's the same formula, except that I've used for the coefficient here, a, the inner product. Now I have an interesting equation. I'm going to read this the following way. I'm going to read this. I'm going to separate it in the following way. I'm going to invent a new symbol. The new symbol is the sum of n times n. What on earth does that mean? We've never defined putting vectors back to back like that. But now I'll tell you exactly what such an object is. When you put vectors back to back like that, any two vectors, it doesn't have to be basis vectors. Take any two vectors. Let's call it a and b. Put them back to back. What you get is a linear operator. You get an operator, and the way that it operates is when it multiplies a vector, you just take the inner product of b with psi and multiply it by a. All right, so this is an object which when you apply it to a vector with the rule that you just take the inner product of b with psi, what you get back is another vector. It's a linear operator. It's called a dyad, a pair of vectors back to back like that. All dyads like that are linear operators. And we can now read off from this equation what this operator is. It's an operator which does nothing. When, let's move this over a little bit. Let's put psi over, well, let's think of this as an operator which hits psi. I have an extra redundant vertical sign here, but that's all right. All right. What does it do? When this construction hits psi, it just gives psi back. So this tells you immediately what the meaning of this object is. It's just a unit operator. How do you read it? When this object over here hits any vector at all, it gives back the same vector. Okay? And that's called, what it's called is the resolution of the identity. But anytime you see this symbol, sum over the vectors of n's back to back like that, it is just a unit operator.
But in that case, n can't be just any vector, right?
N is summed over. N is a sum over a basis.
It has to be a basis.
Yes, it has to be a basis. It has to be a set of orthogonal. We use that here when we calculated that the coefficients were equal to psi times m. We used the orthogonality and the unit character of each one of these vectors. So yes, we did use that. These must be a basis.
Right.
Excuse me. Can you call that the eigen?
This is just the resolution of the identity. That's the word for it.
Yeah, I understand. But if I look at it, it looks to me like it's with an eigenvalue 1.
Yes.
And the eigen.
Yes. The unit operator, every vector is an eigenvector of the unit operator with eigenvalue 1. The unit operator is a special operator that has all its, every vector is an eigenvector of it, and every vector has eigenvalue plus 1. So it's, and it just says that 1 on any vector gives you back the same vector. I is the identity. It's called the identity. Good. All right, but now we might be interested in a subspace. Let's define some subspaces, some interesting subspaces. Subspaces correspond to certain observable questions that you could ask or that you might answer. So for example, let's suppose that we have some operator, some observable, some Hermitian operator that I'll call K. It's something that we can measure. It has an eigenvalue spectrum. It's Hermitian. It has all the properties that we identify with an observable quantity. And let's suppose that we have a eigenvector A of it with eigenvalue lambda. That just says that if you measure K, when the system is in the state A, you will get the answer lambda for certain. Let's suppose there's another eigenvector with exactly the same eigenvalue, not a different eigenvalue, the same one. Different vector, in fact, linearly independent of A, so it's not pointing in the same direction as A, it's not a multiple of A, with exactly the same eigenvalue. Then any linear combination of A and B, let's call it alpha A plus beta B. Any combination like that is also an eigenvector of K with exactly the same eigenvalue. It's easy to check. You just apply K to this, but each term just gets multiplied by lambda, so the lambda comes on the outside. If we apply K to it, the K just goes right through and multiplies each one of these by lambda. The whole thing is just a multiplication by lambda. And so any linear combination of a pair of eigenvectors with the same eigenvalue is also an eigenvector with that eigenvalue. In other words, what we're beginning to discover is that there's a subspace. A subspace, what does a subspace mean? A subspace means a set of vectors which are closed under addition and which have the property that they themselves are a vector space, but might be lower dimensional. Okay. The horizontal plane here is a subspace. It is also a vector space. It consists of all the vectors in the plane here. And basically, it's all the vectors that can be built out of the two vectors in the plane. Same thing here. Any linear combination of these two vectors will be an eigenvector. And so you can talk now about the eigenspace, the subspace, the vector subspace of the original space, which corresponds to a particular eigenvalue. Okay, everybody got that? Two states which happen to share the same property of having a particular value for some particular variable. Yeah. For example, here might be an example. You have up, down, the two-particle system, up, down, and up, up. Both of these have the same eigenvalue for sigma 3. They have different eigenvalues for, I wrote the same thing, up, up. They both have sigma 3 equals up, sigma 3 equals plus 1. They have different values of tau 3, but the same value of sigma 3. Right? Any linear combination of these two also has the same value for the upness or downness of the first entry here. Right? So of course, there's other vectors which down, up, and down, down, which have different values for sigma 3, but these two span a subspace, and it's a subspace in which sigma 3 is up. Okay, good. So that's the idea of a subspace. You could have a collection of vectors. It doesn't have to be two-dimensional. There could be 25 vectors, all with the same eigenvalue, and then 15 others with different eigenvalues. But if you pick out all the vectors that correspond to a given eigenvalue of a Hermitian operator, they form a subspace. They form a linear subspace that if you add vectors, subtract vectors, multiply them by constants, they are still in the same subspace. All right, so what that tells us is that properties such as k equals lambda, that's whatever k happens to be, the property that k equals lambda is not necessarily identified with a single vector, but is identified with a whole subspace. Question? Okay. Now, once you've identified a subspace like this, you can go a little bit further and find a basis within that subspace. So here's some subspace down here. It might have actually, yeah, here's some subspace down here. It's the subspace of the floor. Once we find that subspace, we can find basis vectors in it. Basis vectors that don't span the whole space, but just span the subspace. All right? Good. So just think of the subspace as a space by itself, and we have a set of basis vectors. And I'm just going to call them A's and B's for this particular example over here. Let's call the basis vectors A's and B's themselves. Assume that we found A, B, C, however many we need. It'll be, in general, it'll be less than D. D is the dimension of the whole space, but a set of basis vectors for the subspace, only for the subspace. And those, by definition, have the property that any two of them are orthogonal unless they're the same, otherwise the inner product is 1. So that's delta AB. But A and B now don't run from 1 to D, they run from 1 to whatever the dimension of the subspace is. Good. So we now have the concept of a basis for a subspace. Good. Let's take that basis and construct out of it something which looks like this. Let's take the basis in the subspace and write the expression A. Sum over A. Sum over all the basis vectors in the subspace. What is that object? Right? Now, the first thing I can tell you is it would give you back the same, if you hit any vector with it, it'll give you the same vector as long as the vector is in the subspace. All right? So if we have a vector in the subspace, for all practical purposes, the other directions don't matter, and we're just rewriting this kind of formula over here. If psi is in the subspace, then we just get back psi again. But what if psi is not in the subspace? What do you get? If psi is not in the subspace, then what you get is the projection of psi onto the subspace. So what does that look like? Let's put this vector over here someplace. Sticking out of the blackboard, I don't have enough dimensions to draw it in properly. The projection onto the subspace is the projection of the vector onto the subspace. We just discovered what this object AA is. It's the projection operator. It's the projection operator onto the subspace, which in this case corresponds to the property that k equals lambda. So this object over here is the projection operator onto the subspace, in this case, where k is equal to lambda. That's how you construct a projection operator. If you have a property that you're interested in, you find the subspace which it corresponds to, you find a basis in that subspace. Now, this may or may not be hard to do. I mean, in any particular example, it may be easy or hard, but you find that basis, and then you construct what would have been the identity operator, except it's not really anymore because it doesn't have those vectors which stick out of the plane, which stick out of the subspace. It's the projection operator onto the subspace.
Well, the identity operator is also a
Yes,
projection.
yes, yes. The identity operator is a projection operator. It's a projection operator onto the whole space, onto the whole, on the whole space. If you only had one vector here, it would be the projection onto some particular axis. If you have two vectors, two-dimensional subspace, it would be a projection onto a plane. If you have enough vectors, it actually corresponds just to a projection back onto the whole space. Right? But typically it corresponds to a property. Okay? The property that's associated with the identity operator is a trivial property, just that the system exists. No information is contained. What's that? No, every projection operator characterizes a property. It's the property which is true in that subspace.
Why is it a no change observable or something like that?
I'm not sure what you meant by that.
Okay, I get it.
Okay.
Is this, right, observable is the state. It's in the state of
Right.
existence. Okay.
Final thing about projection operators is the probability postulate. The probability postulate for quantum mechanics is most nicely expressed in terms of these projection operators. And what we can say then is if I give you an arbitrary state psi, which is neither, may or may not be in the subspace, if I give you an arbitrary normalized state psi, then the probability that psi has property k equals lambda is just the expectation value of this projection operator. Let's see if we can make any sense out of that. If I plug in for the projection operator, its expression here, what I find is psi a psi summed over a. Does this make sense? Yeah, it says that the probability to find a particular property is the sum of the probabilities of all the particular ways that you could find that, all the orthogonal ways that you could find that, that particular property. So for example, if the property corresponded to the first spin being up, in other words, if it corresponded to the projection operator onto the first spin being up, let's write down what the projection operator would be. It would be up, 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 plus up, down, up, down. There are two basis states in which the first spin is up, namely up, up, and up, down. And if we construct we're leaving out some things here, down, down, and so forth. But this is the projection operator onto the subspace where the first spin is up. Okay. If I take the expectation value of this operator in any state, it's the probability that the first spin is up, but it comes from two places. It comes from the probability that the first spin is up and the second spin is up, plus the probability that the first spin is up and the second spin is down. Okay. So that's the basic postulate of probabilities. Yeah.
Is the way we interpret these points in the space to be probabilities and the basis vectors of the space to be the observables, or are they the internal space?
No, the observables are the operators which have a collection of eigenvalues. All right? The property of having a particular value is the property that when you measure k, you will definitely get lambda. So the property is characterized by an operator and an eigenvalue. Okay? A projection operator is a tool for calculating the probability that the property is really there. In other words, in this case, it would be the probability that k equals lambda. The projection operator is just a tool, and it's the thing whose expectation value is it gives that probability. Yeah.
A math question. On the left where you have A and B as vectors that have the same eigenvalue.
Yeah.
I didn't understand if those are they always form an orthogonal basis, or you can derive an orthogonal.
Yes, you can find an orthogonal basis. Yes. Do so. Once you've done so, you now can just think of the other directions in the space as being incidental. You now have a space with a set of vectors within it that form a basis.
Over there where you have them as being orthogonal, then you're saying those are A and B are basis vectors in that third equation.
Basis vectors for the subspace.
For the subspace.
Only for the subspace.
Only for the subspace. Would it be correct to label those two bottom axes as A and B?
Yeah, this could be A equals 1. Well, yeah, I have a funny mixed notation here. This could be A and B, yeah.
And then the side would be the one that's sticking up. Or
Psi could be any vector.
and the projection is okay, gotcha.
Right. And then in this case, there's a third vector which does not lie in the subspace. You could add it in as a basis vector for the whole space, but it's not part of the subspace. Okay. Right. And then when you project psi onto A, and then project psi onto B and add the answer, you get the projection onto the subspace itself.
So can I interchange A and B there?
Yeah, and this
When you say K equal to lambda, it shouldn't be uniquely A, right? It could be also B vectors.
Where?
Yeah, you can.
Yeah, in
In
the
which equation?
In the first equation.
This one here.
Yeah.
Yeah. This is just, okay. In this equation here, I'm really talking about a particular vector. Right. In this equation, I'm talking about a sum over vector, so I really should use a different notation. This is a summation variable here, and we can call it sum over A prime or something like that. We can decorate it with as many indices as we want, and it'll just get very confusing. But when you see a sum like this, don't think of a particular vector being picked out. Think of summing over all the vectors. Whereas an equation like this without a summation, it means some specific vector.
So here you are summing over A and B.
Right. This could be a sum over A and B. Right. A prime could stand for A or B, or C or D, depending on how many vectors there are. Exactly. Right. I didn't want to make too many notations. I didn't want to put subscripts on notations, but yes, you've got the idea. A summation index like this here is just a sum over something. Here you've picked out the A vector and the B vector. You could have called it 1 and 2. In fact, that would have probably made more sense to just call it 1 and 2. Okay, any other questions? Yes?
Just to double check, does this say that the probability amplitude?
No, the probability. Yeah. These are probability amplitudes. These are probability amplitudes. Multiplying them by their complex conjugates give you probabilities, and then summing over the different ways that you could get. You see, there are different ways that you could get K equals lambda. You could have it in one vector or the other vector or the other vector. Summing over all the various ways gives you the total probability for K equal to lambda. Does that answer the question? Yeah, good. Okay, good. Just any more? Okay. All right, so that's another way of stating the fundamental probability postulate. Now, if we have two commuting projection operators mean, well, means exactly what I said. Two commuting projection operators. And I'll give you some examples in a moment. Let's call it P K equals lambda, and another projection operator for another property, let's say L equals mu. These are two distinct projection operators for two distinct properties. If they have the property that they commute, then there's some simple definitions that you can make of what you mean by and or. What about and? What is the projection operator for K equals lambda and L equals mu? What is the projection onto the simultaneous condition that both K equals lambda and L equals mu? In order for there to be an and to get any answer, there have to be vectors in common in the two subspaces. I mean, the two subspaces have to intersect with each other. They have to intersect. So if you had two spaces which didn't intersect at all, except at the origin, all subspaces always intersect at the origin. So there's two subspaces which don't intersect except at the origin. Then let's place this one vertically upward, just for simplicity. then clearly there are no states which share the property associated with this projection operator and with this projection operator. There's nothing in common between them. On the other hand, if we had two subspaces which shared another subspace, a lower dimensional subspace, then there are vectors in the space which share both properties, which have the property associated with subspace number 1 and the property associated with subspace number 2, and we can ask which vectors, which states of the system have both property 1 and property 2. And what is the projection operator for the AND statement, for the property k equals lambda and L equals mu? Well, the answer is the product of the two of them. If they commute, the answer is the product of the two of them. Let's see if we can see why that's so. Let me just call this pk. I'm not going to call it pk equals lambda. That's too much notation. Just pk and pl. Now, if they commute, it doesn't matter which order you write them down in. Okay? Let's take any vector, whatever. Let's go back a step. Can I go back a step? Yes, I'm going to go back a step. If you take the projection operator pk and you apply it to any vector at all, whatever, apply it to any vector at all, you will get a vector in the subspace, right? So it stands to reason then that if you take this whole vector here, it must be an eigenvector of k with eigenvalue lambda. This is a vector in the subspace k equals lambda. And so it must be the case that k on this just gives you lambda times pk times psi. This isn't very deep. It just says that pk on psi gives you a vector in the subspace where k is definitely equal to lambda. Okay, now let's take the product, pk times pl, apply it to any state whatever. I say that this vector will have both the property that k is equal to lambda and L is equal to mu. How do we check that? Well, first of all, I told you that if you take any state and multiply it by pk, it'll have the property k. By property k, I mean k equals lambda. Let's just call it the property k. Any vector, if you multiply it by pk, has the property k. Well, here's a vector. I've multiplied it by pk on the left. Therefore, it has the property k. But if it's also true that pk and pl commute with each other, I can also write this as pl times pk on psi. And now I exhibit the fact that it has the property L. So if I have two commuting projection operators which commute with each other, that roughly means that the two observables are compatible with each other, that you can measure both of them independently, that you can measure them both simultaneously, then the product of the two projection operators corresponds to the AND statement. In other words, it corresponds to vectors, or it corresponds, to the projection onto the simultaneous property k equals lambda, L equals mu. For example, if I wanted to know the probability that k equals lambda and L equals mu, it's just the expectation value of the product. Right. Psi, pk, pl, psi is the probability not just that k equals lambda or that L equals mu, but that k equals lambda and L equals mu. Okay? That's the AND statement. You multiply projection operators. There's also an OR statement. The OR, yeah. Also known as, well, in classical logic it would be the intersection. I'm not sure that you call it the intersection in vector spaces, but it is the intersection in that sense, yeah. In classical logic, it would correspond exactly to that, if you have a property described by a subset of points in a set, and you have another property, then it's the intersection which corresponds to the or statement. Sorry, the and statement. The or statement corresponds to the sum of the two projection operators. I'll let you try to prove that yourself. And is product, or is sum. So if you're interested in what vectors either have the property that k equals L, that k equals lambda, or L equals mu, the or statement, then the projection operator happens to be the sum of them. But we're going to be more interested, I think, in the product. If they're not compatible, you just get hash. You can't measure both things together. I think it's clearest if they're compatible. If they're not compatible, you can still define it, but it's not a very good definition. What's that? Okay. The spin of one, if you have a two-electron system, any component of one spin is compatible with any other component of the other spin. Okay. We could check that.
How about spin and charge?
Spin and charge, this could be another one, yeah. All right, but let's check, let's take the case of two spins. You have a bunch of, let's see, yeah, because the spin operators act completely independently on the two sets of degrees of freedom, they always commute with each other. If you first multiply this vector by some sigma and then multiply it by a tau, you get exactly the same answer as if you first multiplied it by tau and then sigma. So usually, very often, compatible operators are simply operators for two separate subsystems. When you build subsystems by putting systems together, any quantity associated with one subsystem is automatically compatible with the quantities for another subsystem. That's an example.
But subsystems, you really sort of mean degrees or types of freedom, dynamical degrees of freedom.
Yes.
I mean, I'm thinking of momentum and spin, for instance, and those were...
Well, momentum and spin happen to be compatible. Yeah. Yeah, but they could belong to the same electron. But if you had two distinct electrons, then anything associated with one electron is automatically compatible with the other electron. On the other hand, there can be things associated with a single electron that are compatible. For example, if an electron is moving in three-dimensional space, the components of position, x, y, and z, are also compatible with each other. We haven't spoken about that because we haven't done that kind of quantum mechanics. We're doing bit quantum mechanics and not particle quantum mechanics. But the simplest situation for compatibility is when two things belong to two different, let's call them qubits. In the case of qubits, in the case of simple spins, the criteria would be that they belong to different spins. They're associated with different spins. Then they're compatible.
You make it sound like everything's compatible.
No. Something good, something which is not compatible would be the x component of one spin and the y component of the same spin. Okay. You can't measure the x component of a spin and the y component of the spin at the same time. So they're not compatible. Okay. You only got one direction that you can put the magnetic field in to measure the spin of a particular electron. You can't put the magnetic field simultaneously in two directions and try to measure two different components of the same spin. On the other hand, if you have two electrons, and the simplest situation is just take them apart, put one magnetic field over here in one direction, another magnetic field over here in another direction, and you can measure two different components of two different spins. So they become compatible, but two components of the same spin are not compatible.
So excuse me, that just is the same way as saying the different sigma matrices, they don't meet, right?
Yes. It's just a statement that sigma matrices don't commute. Is that what you said?
Yes.
Yes.
So when you see these two sigma matrices not commuting,
Yep.
that proves that
That's all you need.
the
That's all you need.
actually
Absolutely. Absolutely, yeah.
The position and momentum don't commute.
Position and momentum don't commute.
That's another example.
Right. Position, although the position, yes, position and momentum don't commute. Right, exactly. All right, so we have the concept of and then let me just remind you, I just wanted to go through this again to make the logic clear, what we did last time. I sort of implicitly pretty much assumed everything that I've done tonight when I described it, and it may have left you less than comfortable with the procedures. Let me just remind, we're not going to go through the calculation again. Just going to remind you what we did. This was the Bell inequality. Well, first of all, we proved the completely classical theorem. The completely classical theorem had nothing to do with quantum mechanics, and it's not even true in quantum mechanics. It says if we have some properties A, B, and C, then the number of objects which have A but not A and not B, plus the number of objects, and the number of objects could also stand for probabilities. Number of objects with B but not C is greater than or equal to the number of objects with A and not C. Now we can apply this to, if electrons were strictly classical objects, we could apply it just to electrons and take A, B, and C to be the following quantities. A could stand for electron, the Z component of the electron, the third component of the electron up. And I'll just indicate it by pointing an arrow up. That's A. B could be that the electron is pointing along 45-degree axis in the 1-3 plane, to be simple. And C could be that the electron is lying along the horizontal axis, that if you measure along the horizontal axis, you definitely get up. Not A, B, and C, or in particular not B and not C, would correspond to the electron pointing in the opposite direction. So if B corresponds to electron pointing in this direction, then not B corresponds to it pointing in the opposite direction.
Can I ask a question about, say up and down?
Yeah.
You can have up and down or orthogonal,
right.
But up is not minus down.
No, it's
They're
not.
two different things. Okay,
That's
what
right.
is that minus, and that just, plus and minus just something that happens in the calculations?
Yes, absolutely.
And doesn't have a physical...
Well, it sometimes influence. The vector A plus B might be quite different than the vector A minus B. And I gave you an example. Up, down, minus, down, up is quite different than A, up, plus. You know, the sign can make a difference, but the overall sign never does.
Okay.
If Bell's theorem gets violated for any quantum properties of anything, or only for certain ones, and in which cases?
I don't honestly know the complete answer to that question. It's certainly not violated for any state. For example, I can find states of the two-particle electron system for the Bell inequality will be satisfied, for sure. So the answer is that there are certainly states for which the Bell inequality is satisfied. You have to search a little bit to try to find situations where it's violated, but it's not very hard. If you just just take a random guess, I don't know, 60-40, 60% of the times you'll satisfy the inequality, 40% you won't. I just made that up. I have no idea really, but most likely, I would guess that it's more likely, if you've randomly selected a state, that the inequality would be satisfied. And that it's a sort of a smaller percentage of the space of states that doesn't satisfy the inequality. But I never checked that. That's something...
You can set B up to be at an angle theta to A.
Yes, you could. You could. And then you could check it. You could check it as a function. Yeah. 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 And you could also have C be an angle. And I would guess if the angles are too close together that you don't violate the inequality. But we can check that. That's an interesting thing to check. At what angles is the inequality satisfied? At what angles is it violated?
If they're 90 degrees apart, if some integers are multiple of 90 degrees, then you don't have any problem.
Could be. Yeah, I haven't checked it, but you're talking about photons, I think. Talking about photons or electrons? Okay, so that's a little bit different, but yeah. Yeah, there's certainly situations where the inequality is not violated. But let me just remind you what we did. All right, then what we did was take a 2-electron system, and we imagine doing many checks. The 2 electrons are in the singlet state, and we do many checks on this, and every single time we find out that when if we measure the spin of one of them along any axis, the spin of the other one is along the opposite axis. That would suggest that the property not B for electron 1 is the same as the property B for electron 2. In other words, it would suggest that the property not B, which says that electron 1 is down, is equivalent to the property B for electron number 2. Okay. So we could rewrite this inequality then as, if we work in terms of pairs of electrons, we have these pairs of electrons which have been created. They've been created in a way that the spins are always anti-aligned, and we can substitute for the property A and B. We can, first of all, A can still be associated with electron 1. A and not B would then become the number of pairs where the first electron is up, but the second electron is at 45 degrees. The second electron being at 45 degrees would imply that the first electron was in not B, if it made sense to talk about A and not B for electron number 1. So that's this one over here. Let me...
I'm sorry. Not B should be minus 45? The other direction?
Not B means the electron is pointing this way. But if electron 1 is pointing this way, electron 2 is pointing along B. So not B for electron 1 is B for electron 2. All right? Good. All right. Not something for electron 1. Since they're opposite, any not statement for one becomes the positive statement for the other. Good. All right, so we can now rewrite this inequality as the number of pairs in which the first spin is up, but the second spin is along 45 degrees, plus the number of pairs in which the first spin is at 45 degrees, but the second spin is at 90 degrees, is greater than or equal to the number of pairs where the first spin is up and the second spin is at 90 degrees. All we have to do to check the inequality for any given state is to construct the projection operators for these properties. Now, this is a 2-electron system now. We've replaced the 1-electron system by a 2-electron system. If we were doing classical physics with classical logic, the opposition of the 2 spins would tell us that not B is the same as B for the second spin. So that's the logic here. Now, okay, so what are the projection operators? We take any state, whatever, and we can ask, what's the probability for this property? What's the probability for this property? What's the probability for this property? So let me go back now. We want to construct the projection operator for this property. This property has spin number 1 pointing up. The projection operator for that is 1 plus sigma 3 over 2. If the first spin is up, sigma 3 gives plus. 1 plus 1 is 2 divided by 2. That's 1. Okay, so yes, that's if this first spin is down, then sigma 3 is minus 1. 1 plus minus 1 is 0, and we get 0. So this is the projection operator onto the first spin up. The projection operator onto the second spin pointing along its axis is also a 1 plus something, but not 1 plus sigma, but 1 plus tau, because tau is the spin operator for the second electron, but not tau along the third axis, but tau along the 45-degree axis. What is that? That's tau 1 plus tau 3 over the square root of 2. That's the projection of tau onto the 45-degree axis, and then we should divide it by 2. This is the projection operator for one statement. Spin number 1 is up. The projection operator for the other statement, spin number 2 is along 45 degrees, is this one. What is the projection operator for the AND statement, that electron number 1 is up and electron number 2 is along 45 degrees? It's the product. Okay. It's the product, so we multiply these two operators together. Dot just means multiplication. Right. We do the same for this one. Same kind of thing for this one. I should move this over a little bit, but the second projection operator, let's put it over here, would be the first spin along 45 degrees. That's 1 plus sigma 1 plus sigma 3 over square root of 2, all divided by 2. But then the second spin along the horizontal axis. So that's 1 plus tau 1 divided by 2. That's the projection operator for the second configuration. And the projection operator for the third configuration is 1 plus sigma 3 over 2 times 1 plus tau 1 over 2. Well, we know how to work with these sigma and tau operators. And if I give you any state of the two-electron system, you can calculate the expectation value of these three projection operators. And you can simply check, is the expectation value of this one plus the expectation value of this one bigger, or is it not bigger than the expectation value of this one over here? This is the exercise that we did last time for the singlet state. For the singlet state, up, down, minus, down, up. And we found that the inequality was violated. There is no reason why it should not have been violated. We're not doing classical set theory. The derivation of this formula here came from drawing various classical sets and looking at the, just counting up what things corresponded to A and not B, what regions corresponded to A and not B, what regions corresponded to B and not C, what regions corresponded to A and not C. It didn't have to do with the intersections of projection operators. It had to do with the intersection of sets. So there was no reason why the inequality should have been satisfied in the quantum context, and it's not. Yeah.
If we know that for a particular system, the Bell's theorem either violated or not violated.
For a particular system in a particular state.
Right, in a particular state.
That's right.
Then is there anything more we can say about it, or nothing?
The only thing you can say about it is this is a very clear demonstration that quantum mechanics cannot be the statistical theory of some kind of system with classical, that's really governed by classical logic, by classical set theory. That's all that you learn out of it. That it cannot be, and
so if a particular quantum state actually satisfies Bell's theorem, can we say that it's some sort of, it's more classical than not in any way?
I think you probably, maybe. Remember, there are many, many variables that you could check. In this case, well, Bell's inequality you may be able to check very, very many different inequalities for the same system. So by choosing properties, by choosing a particular set of three properties, you might find for a certain system in a certain state that the inequality is not violated, but then choose some other properties for the same system, you might find it is. And I suspect that would generally be true. I think that would probably always be true, that you could probably always find properties A, B, and C that the inequality would be violated.
There's a later kind of...
Okay. I'm having difficulty trying to figure out what kind of an experiment this describes. How many magnets and populations of electrons and...
Yeah, good. Okay. So that's the right question to ask at this point now. We have a beam of particles, but the particles come out in pairs. They come out in correlated pairs. Here's how we might start. We might start with a pair of electrons The pair of electrons are near each other. Because they're near each other, they interact with each other. And the lowest energy state happens to be the singlet state. And so after a while, they either do or don't emit a photon, but they get into this singlet state. Then the electrons are taken apart. And that's not too hard to do. I mean, you can send them through some sort of system which separates them. It could be an electron and a positron. You put them in a field. The field sends the electron one way, sends the positron the other way. And so you have a well-separated pair. But not just one of them, many such pairs. For each pair that you've made, there they are, you measure, divide them up into groups. Divide them up into groups so that we can do 3 separate experiments, okay? So we have 100 billion pairs. We take a third of them, and on the third of them, we're going to measure the number of A and not B. How much is a third of 100 billion? 100 billion divided by 3. We take 100 billion divided by 3 of the pairs, and in the first set, we measure the up component of the electron, the vertical component of the electron, and the 45-degree component of the positron. Okay? And we count up altogether how many pairs are there in which the first electron was up along the 3-axis, and the second electron was up along the 45-degree axis. Count them, and that gives us a probability. That gives us the probability, forget n's, we can just use probabilities here. That gives us the probability that the first electron is up and the second electron is along 45 degrees. Then we take the second group and do exactly the same thing, except in the second group, we don't measure the first electron up and the second electron at 45 degrees. We make the second electron at 45 degrees, the first electron at 45 degrees and the second electron at 90 degrees. We count up the probability for that. We add it. And then finally, we take the last third of the electron pairs, of the electron-positron pairs, and measure the first electron up along the z-axis and the second electron along the horizontal axis, and count how many of them have the property that the first electron is up, or what percentage have the probability that the first electron is up and the second electron is horizontal. The theorem says, classically, if it were true, it would say that this plus this should be greater than this.
But your theorem is dealing with a single population, and this is 3 different populations.
You can take it as dealing with probabilities. You can take it as dealing with probabilities. And since we have a identically selected set of 3 populations, we can measure the probability distributions by looking at just the separate. The theorem would be true if we divided the system identically prepared, assuming they're identically prepared, all 3 populations, in fact, every single pair here, the theorem would be true about these subpopulations also.
It doesn't matter that they came from some sort of a superpopulation to begin with. You could have gone all
as long as you prepared them in the same way. That's right. As long as you prepared them in identical ways. So, yeah.
In the year 2000, Alan Aspect wrote an article commemorating John Bell. In there, there's this very neat diagram that shows basically the distribution that you can expect classically versus what you get quantum mechanically. And it shows how the quantum mechanical results include some data points which are outside of the classically or inside the classically excluded region.
I haven't seen it, but 1980 or 19 when?
2000.
No. Alan Aspect.
I don't understand why you can't use this to signal. The 2 electrons would be going apart very slowly. And so, if Alice measures one of them, if they're going across slowly, you could measure it and then send a message at the speed of light saying, I just measured this, expect yours to arrive.
Right, that was, as far as I understand, Aspect's experiment was done in such a way that the two measurements could not, that a light signal could not have been sent between them. Yeah. Yeah. If there was time for a light signal to go from one to the other, then it would not be a contradiction. You might wonder, how the hell did the signal get across there? What was the mechanism? Who sent the light beam and so forth? But you wouldn't have a contradiction with causality or with locality or whatever you want to call it if the second electron was measured after a time during which a light beam could have gone from one place to another. You might say, oh, I didn't see any light beam go. I must have discovered some new force of nature that I didn't notice before, but at least it doesn't exceed the speed of light. But the trick is to do the experiment in such a way that a light signal could not have gone to the second electron when you measure it from the first electron. I don't think he used electrons. I think he used photons, incidentally. But you know.
I think the way Aspect had put it was that in order for the classical explanation to match the quantum mechanical prediction, the signal would have had to travel faster than speed of light.
Right, right. That's the other way to say it. Right. And that's right. That's exactly right. So part of this whole queerness of this entanglement is connected with signals not going faster than the speed of light. When people say that in order to have hidden variable theories, and that means classical logic systems which can somehow mock up the effects of quantum mechanics, when they say they have to be non-local, what they mean is that signals have to be able to go faster than the speed of light to send messages between the two electrons. I want to get to another thing, and we're not going to get to it, but yes, we are going to get to it, yeah. I'm not giving you any freedom to run loose in the hallways. There's nothing sacred about the...
There's nothing here that...
No. That's right. There's nothing sacred about conserved quantities in this context here. It's just a nice, very simple system to work with. In fact, these don't even really have to be spins. They could be any two system, any system that has two states, an upper and a level atomic state.
Energy itself is being subject to this.
Yeah. No, it was not important that this was that spins are angular momenta or anything like that. No, not at all. All right, what I wanted to do next was to talk about the connection between three things: interference phenomena, measurement phenomena, or how you do what a measurement means, and its connection with entanglement. How a measurement is really the establishment of entanglement between systems. That's what a measurement is. And how measurements destroy interference. How they, and it's called the collapse of the wave packet. So I thought we would get to that next. And let's see how far we can go. We may want to come back to it if I don't... So what we're actually going to be speaking about is the two-slit experiment. But I'm going to simplify the two-slit experiment so that we can think about it as just having a finite number of states, a little simpler than the two-slit experiment. It is the two-slit experiment. But we'll just imagine that a photon or an electron, or whatever it happens to be, no spin, forget spin. Now these are real particles. They really move from one place to another. But let's suppose that the particle could be in any one of several vertical locations. Just to make life simple, some set of, we'll call this 0, 1, 2, 3, minus 1, minus 2, minus 3. So the electrons, I'll call it an electron, but forget its spin. It starts out at 0, and this is the position of the electron along the vertical axis. The electron is actually going to move to the right, It might also move up or down, but I'm just simplifying by giving it only a finite number of places where it can live, just so that we can use the tools that we've been talking about of finite dimensional spaces. So the number of possibilities where the electron can be is finite, in this case 7 of them. All right, the electron moves over to the right. There are also 7 places where it can be found over here. Actually, from this side over here, I'm going to select out and assume that the electron started at this point here. So the electron actually starts at 0. Right? Now, it goes over to here, and when it gets over to here, it's in one of these 7 places. Depending on which place it's in, well, not depending on which place it's in, it continues to go. And it continues to go over to a 3rd place, which also has the same set of 1, 2, 3, 4, 5, 6, 7, the same set of possibilities. Right? We're really talking about the evolution of a system from one instant of time to another instant of time. But here's the game we're going to play. It is the 2-slit experiment. I'm going to assume that if the electron arrives at this point, that it just gets sent back. All right? So we're going to ignore the possibility that electrons which go backward. If it goes to this point over here, it also goes back. It only goes through if it hits this point or that point. So from the point of view of a 2-slit experiment, I've opened this slit and I've opened that slit, and I've sent an electron to here or to here, 1 electron at a time. We're sending 1 electron at a time. It either goes through the upper slit or the lower slit. And if it goes through the upper slit, it can go through either slit and arrive at any one of these places over here, and so forth. All right. I'm interested, I'm going to give you some, we're going to make up some rules that are consistent with quantum mechanics. A simple example. I'm interested in the end in the probability that the electron arrives here, 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 or here, or here. What's the probability under various circumstances? Now, here's the assumption. The evolution of systems, the quantum mechanical evolution of a system is linear. That means that if a system starts in the state A and evolves to a state A prime, in this case it could be that it starts at any one of these places here and gets to any one of these places here, and if the state B would evolve to B prime, then if we start the system in the state A plus B, it will evolve into A prime plus B prime. This is the assumption of linearity. In fact, we can do this with arbitrary coefficients, alpha, beta. That's the statement that states of systems evolve in a linear way, that linear superpositions evolve into linear superpositions. Now, this is an experimental fact. As I said last time, it's very, very hard, maybe quite impossible. Nobody has ever succeeded in changing quantum mechanics a little bit without coming to really silly conclusions. So we'll take it as a postulate that the evolution of state vectors is linear. Linear superposition evolves to the same linear superposition with the same set of coefficients. All right, that's about all I'm going to assume, and we're going to, well, make some definitions now. I'm going to start the electron over here, and after a certain time, it will have arrived at one of these places. I'm not interested, I might as well throw away all the places which just reflect the electron backward, because I'm not even going to look for it back here. So it either gets to 1 or to -1. And by symmetry, just the up-down symmetry here, if I really do have enough up-down symmetry, if the length of this path is exactly the same as the length of this path and so forth, and I start the electrons symmetrically, about the only state that I can get to over here is the linear combination. So we can write it this way. We can say, starting with 0, the state will evolve to the state 1 plus -1. Now, I'm not terribly interested in normalizing the state. I'm not interested in keeping track of total probability here. That's not going to play any big role in what we're going to say. So if we start with the electron over here, after a time, by the time it gets to the slits over here, it will be in a superposition of states with equal amplitude, with equal likelihood of being here and here. Just because of the symmetry of the problem, you would expect equal coefficients here. But now let's say, what happens if an electron starts at 1? What happens to it when it goes over to this side over here? So let's make a postulate or an assumption about that. If it starts at 0 initially, it gets to 1 plus 1 prime, or minus 1, 1 plus minus 1. What happens if it starts at 1 over here or minus 1 over here? What happens to the state vector over here? So let's make the following assumption. If you start at 1, if an electron starts at 1, then by the time it gets over, we can call this the screen over here. That's where we measure the electron, the screen. By the time it gets to the screen over here, I'm going to make an arbitrary assumption that it is in the state summation psi n n. It has to be some linear combination of, these are basis vectors, they correspond to orthogonal configurations. These are different places, they don't get mixed up with each other. If an electron is over here, it's not here. If it's here, it's not here. So we have these basis vectors n, and this is about the only thing I can write down. Sorry, not 1 is equal, but 1 goes to. That 1 becomes, after a further interval of time, it becomes some linear combination.
But it's not the same state either. I mean, you got.
It's not the same state.
You got n there and you got a 1, but you really mean two different. Your notation is not distinguishing between the second and third panel.
Between where and where?
So you've got a 1 for your.
This one corresponds to starting over here.
Like you would put primes or something like that on your mathematics on your statement over there.
Over here. Yes, I could, but I didn't want to decorate it with too many symbols. So just this goes to just once I put an arrow there, I don't have to be so. I'm not writing anything as equal to anything else. I'm just saying the state 1 over here will evolve into some state psi n times n. What happens if it starts at minus 1? Well, if it starts at minus 1, it'll go to some other combination. I'm not even going to tell you what combination it is other than to say it's some other phi n times n minus 1. These are arbitrary linear combinations over here. They could be determined by experiment. They might be determined by mathematics. But I've written down the most general possibility that if you start at 1 over here, you will get to some linear combination characterized by a set of coefficients. If you start at minus 1, you will get to some other linear combination. I won't even tell you what they are. What happens if you start in the initial state 1 plus minus, the linear combination of both of these? Then the linearity postulate tells you that at the end, the final state will be the sum over n of the sum of these two, which is phi n plus psi n times n. In other words, by the time you get over here, the coefficients will be the sum of the coefficients that you would get by going through the upper root and going through the lower root. All right? If you go through the upper root, in fact, even if you closed off the lower root, then the experiment would only involve 1 going to psi n here, if you closed off the lower root. If you closed off the upper root, the experiment would only involve going from minus 1, would involve this combination over here. If you open them both and allow the electron to go either way, then the rule is the linearity of quantum mechanics tells you that you should add the state vectors. If you start with a linear sum of two vectors, you should add the two in the final state. So you get to here.
Question?
Yeah.
Are those normalized on the right side side?
It doesn't,
Because if they're
they
not,
could be.
if one of them is way bigger than the other, it doesn't make any sense. You've got to do something, it seems to me.
Why doesn't it make any sense?
Well, I mean, psi n could be in the billions, and phi n could be very small if
It
they're
could
not
be.
normalized.
It could be. For example, if you put some obstruction here which only let very few electrons through, we could make the phi's be much smaller than the
I'm just
size.
suggesting that you haven't said what the units are. I mean, one could be in meters, and
What? Wait. Size and phi's are dimensionless objects. They're squares of probabilities.
I know, but they have a scale. They have a scale factor associated with them that you normally take out.
Yeah, we can normalize them.
I see.
I didn't bother normalizing them over here. At the moment, I didn't want to worry about keeping track of total probability. All right, that's something we'll do next time. That's called unitarity, and I don't want to worry about it right now. Whether it's normalized or not normalized is not so important. The important thing is that that you get the sum of the coefficients going through the upper root and the lower root, and that's the postulate of linearity, that if you evolve from 1, you get psi. If you evolve from -1, you get phi. If you evolve from the state 1 plus -1, I don't like to say 1, for this state plus this state, then you get the sum of the two. That's the postulate of linearity. What's the probability then, at the end of the day, that you measure the electron at the nth or the mth site? Well, these are the coefficients that add up to give you the state vector. This is an orthonormal basis. It's quite clear that the probability that you'll land on the mth site over here is just psi m plus phi m complex conjugated times psi m plus phi m. We could either do this through projection operators or just use the simpler statement that the squares of the coefficients, we take the coefficients here, we complex conjugate them and square them, and that gives us the probability that we arrive at the mth site. M could be 1, 2, 3, and 4, and this would give us the various probabilities for arriving at different places. Notice what we get. We get 4 terms when we work this out. We get psi star of m psi of m. Now what is that? That's all we would have if we closed off the second hole. If we only had the first hole open, the answer would just be psi star m psi m. So what this is the probability that had we closed off the second hole, we would have arrived at the nth place. On the other hand, there's also phi star phi. That's the probability that if we closed off the top opening and went through the bottom one, we would have arrived at the nth place. Classically, that's all there would be. The probability to go from here to here by one of 2 routes would just be the sum of the probabilities of going through the upper root and the lower root. That's all you would have in classical physics. If you had a random walking particle that random walked around, you left the upper hole open, you would have a certain probability to get here. If you left the lower hole open, you would have a different probability to get to the same place. If you left both holes open, the probability would just be the sum of the 2 probabilities. But in quantum mechanics, we have 2 other terms. Psi star m phi m plus phi star m psi m. Do I have that right? Yes. Let me give you an example. Let's consider the probability that we get to the symmetric point over here. For the symmetric point, we might imagine that's 0, that's m equals 0. M equals 0. We might imagine that psi and phi are equal to each other. Why? Because one of them corresponds to going through the upper hole, the other one corresponds to going through the lower hole, but by symmetry, we might just assume that the amplitude to go from here to here is the same as the amplitude to go from here to here, and it would be. And in that case, psi and phi would be the same. In other words, if we plugged in 0 over here, the probability to get right to here, to the central point, 0, 0. The whole answer is 4 times the probability that you would just go through the upper hole if only the upper hole was open. Now that's odd. You would have expected classically just twice the probability. If you opened up both holes, you would expect that the answer would be twice the probability to get to here, not 4 times the probability to get to here. All right. But what you get in quantum mechanics in this case is 4 times the probability, and the reason is because you add up the amplitudes and then square. If the amplitudes are equal and you square, you'll get 4 times the probability. Okay. That's a little bit odd. All right, maybe it's not that odd, but let me give you something even odder. By putting in the right little apparatus over here, you could make changes in the system, basically just a little potential or something that would have a little bit of effect on the electron as it went from here to here. It could have the effect of changing the sign. It could have the effect of changing the sign. If it changed the sign, it would also change this one. In that case, if psi of 0 was equal to phi of 0, they would cancel. And you would find 0 probability to get to this point over here. This is destructive interference. The 4 was constructive interference. The 0 is destructive interference. And what does it say? It says that there are situations where, with a certain probability, you would get to here going through the upper root. With an equal probability, you would get to here going through the lower root. But if you open up both roots, you make it impossible to get to here. Okay? That's at least, for my money, that is as odd as the Bell inequality. That by opening up, you would think you make it easier to get to here, and in fact, you completely block out the possibility of getting to here if you start with the minus sign here. Okay? But the minus sign doesn't affect either of the probabilities for the upper root or the lower root. It only affects what happens when both roots are open. When both roots are open, it becomes completely impossible to get to here, despite the fact that if you only opened one root, block this one off, you can get to here. Block this one off, you can get to here. Equal probabilities. Open them both, no electron will ever get to this point over here. That's destructive interference. So it's clear that probabilities in quantum mechanics are not doing the things that they do in classical mechanics.
Can I ask a question about that? Regarding locality, let's suppose those two holes of 1 and -1 were some distance apart, and you could, in a time less than it would take light to go from one to the other, turn on that little field so that you would change it from constructive to destructive interference in a very short amount of time, so that when an electron was going from the source to the middle screen, it might be constructive, but then just as it was getting there, it would return to destructive, and then you would accumulate the results. In other words, you're changing the experiment so fast that you can't, the electron couldn't know. I think my thought is, even if you change it fast, you would still get the proper result, such as, you have interference, you have...
Well, I would say to change the sign, you might want to do something in the leg over here. Right. All right. Right. So, right. Well, right. You could do it while it's in flight, but then it would depend on whether you made the change before the electron got to here or after the electron passed it.
Just right prior to it, but in a smaller amount of time.
Well, the electron is over here?
Yes, and so that when you made that change there, that nothing could propagate at the speed of light to the other slit.
Over here? No, to the other slit.
Yes.
No, I think if you make the change before the electron gets here, you've made the change.
Right.
And that will change the sign here.
Right.
That will change the sign.
I think his point is that in a delayed choice type of an experiment where you open or close the slit in a random way that wouldn't permit somehow the correlation to be set up at the other slit, the quantum mechanical result is still going to hold. Classically, you would have to have some kind of, in order to get the correlation that you actually meant to find out.
Well, we have no correlation here, just a probability, just a pure probability on the side, a probability distribution. Right. It's not just that the probability depends on whether there's one slit or two slits. Of course it does. It's that the probabilities don't add. It's the probabilities don't add, the amplitudes add. The probabilities don't add. You get a probability in either case, depending on that sign, 4 times bigger than the probability to go through one opening with the other one closed, or just 0.
Right, but you can come back and decide and figure out which way, which of the 2 wave functions was the actual description at the time, and you would find that the results, the distribution that you get corresponds to that, the thing that you discovered later on is the actual situation at the time. It's a weight choice experiment where you don't know what you're going to do until it actually happens. So whether it's a plus or a minus sign depends on some setup of the system, which is space-like separated from the other part of the system. And then later on, you go back and reconstruct what happened.
Well, I think you'll have to give a more precise setup in order. I'm trying to study very, reasonably precise setups, and we would have to investigate each one separately. But what I really wanted to get to, we'll see if we can get to it, I don't know, we're probably going to come back to it, is what happens if somebody over here, if there's an apparatus over here which monitors which way the electron goes through, which measures and records which way the electron goes through. This is the interesting question. Here, I have assumed that nobody has recorded which way the electron has gone through. So at the end of experiment, you can't really say the electron went through here or you went through here. You don't know which way it went through, and there's no clear notion of being able to check afterwards that the electron went through the upper or the lower hole. But supposing you set the problem up in a way that afterwards you can check. There's something which records whether the electron goes through the upper hole or the lower hole. Then what happens to the probability distribution? Well, you might think, well, who cares whether you measure it or not? Careful, measure it in such a way that doesn't disturb anything very much. Do some very minimal, gentle detection of the electron, whether it goes through there or not. You shouldn't disturb the system very much. But in quantum mechanics, it's not always possible to do minimal, gentle experiments. And if you do an experiment which does record which way the electron goes, you will change the answers in a rather dramatic way and basically destroy this interference, basically destroy either the positive interference or the negative interference. And so let me show you how that works. And this is an issue of entanglement. This is entanglement of the electron with the apparatus which measures it. So let's invent an apparatus. It's a very simple apparatus. When the electron goes through the upper hole, well, let's just put an upper hole over here, a lower hole over here. The electron either goes this way or it goes over here. And here's my assumption. If the electron passes by this hole, well, we're going to put an apparatus. The apparatus is going to be very simple. It's going to be a spin. It's either up or down. This spin is either up or down along the third axis. We're going to start with a spin down. If the electron goes through the upper hole here, it records its presence by flipping the spin up. Right? If it goes through the lower hole, it does nothing to the electron. This is the apparatus which records which way the electron goes. One extra spin It could be another electron, or it could just be some abstract system with two states. And if the electron goes through the upper hole here, it records its presence by flipping the spin to up. All right, let's do that problem. I think we'll see if we can get the problem done, but we will go through it again, I think, because it's probably the most interesting.
You put a detector in the other hole too?
What's that?
Did you put a detector?
We could put a detector in the other hole too, but I don't think we need a detector in the other hole, because if it doesn't go through here, it does go through here. So we would have a funny situation. We would have a very funny situation if we put a detector at both places and both of them didn't record, but the electron got over to here. So presumably that's forbidden. You really only need a detector in one place to tell you that the electron either did go through here or it didn't go through here. Because it's an electron. Electron can't go through both. It's not big enough to go through both. Either goes through one or the other, right? If you measure it, it will go through one or the other. Right. If you monitor it, you will find that it goes through one or the other. If you don't monitor it, there's no way that you can know which one it went through. If you do monitor it, at the end, you can go back and check that electron. Now, you could put another one over here, too, and analyze it, but that way we have two electrons, and it gets a more complicated apparatus. But we could certainly do it. It'd be fun to do it and see what we get. But OK, so let's then start. We start with the electron over here. It starts in the state 0. But that's not enough information. We also have to specify the state of the spin. So now this is a composite system composed of two parts. The electron, which can be at any one of these sites but happens to start at 0, and the spin. And the spin starts down. So let's put in the coordinate of the spin here. That's the initial state, spin down, electron at 0. The electron comes over to here. Now, what happens if it goes through the upper state? Let's close off this one and forget it for a moment. If it goes through the upper configuration, then the electron comes out, or the configuration of the whole system, forget the electron, the whole system then comes out in the state 1. That's because this is position number 1. This is position number -1. It comes out 1, but what happens to the electron, to the spin? It's up. So if we go through the upper hole, the state of the system is 1 up. What happens if we go through the lower hole? I hate this notation, 1 and -1. I should not have done that. -1 and down. I'll put a comma in there. What happens if I open both holes? If I open both holes by the linearity of quantum mechanics, the state that comes out the other side here is the sum of these two. 1 plus configuration of electron at -1 with spin down. Okay. So by the time the electron comes out, or the electron arrives at this point, and again we have a superposition of states, but notice that it's entangled now. The position of the electron has become entangled with the spin. It's very much like down, up, plus up, down. We have an entanglement between the recording apparatus and whether the electron went through the upper hole or the lower hole. Okay. That's what a measurement is. It's a entanglement between the apparatus, and the apparatus is just an electron spin here, and the system being the position of the electron that went through. All right. Now, what happens after that? What happens by the time it gets over to the screen over here? Let's see. Let's use this blackboard. Well, let's assume that nothing happens to the spin. If the spin is up, it's up and it stays up, but the electron proceeds to do exactly what it would have done after it passes through here. All right. let's assume that it just continues on its way, leaving the spin up. But remember, previously, 1 went to summation over n psi n n. That's what we found over here. Well, if nothing happens to the spin during the journey of the electron over to here, we can just stick in the spin coordinate and just say electron in the upper configuration with the spin up evolves exactly as it did before without the spin doing anything. The spin just stays up. What happens if we start with the electron in the lower state here? That was -1. That evolved into some phi sub n, n. But now we should put in the coordinate of the spin, d, d. What happens if both roots are open? If both roots are open, then the final state is sum on n, psi n with n up plus phi n with n down. Again, it's an entangled state. The coordinates of the position of the electron are entangled with the apparatus, with the upness and the downness. We can now calculate. I'm getting a little bit tired. I think we'll probably go on next week. But here's the problem. What is the probability that we arrive at a particular n? Now we have a different situation. We have 2 orthogonal possibilities for the spin. Okay? To calculate, well, I'm going to quit now because I think I've probably given you more than enough for tonight. Here's our problem: to calculate the probability that we've arrived at the mth site. In particular, the probability that we've arrived at the origin, 0. Right? Anybody know what the answer is going to be? Just the sum of the 2. And the reason is there are no cross terms, because the cross terms involve the inner product of a down with an up. And the inner product of a down with an up is 0. The cross terms won't be there anymore, because when we go to calculate the probabilities, ups and downs are orthogonal to each other, and the cross terms will not be there. I'm going to go through this. I'm going to go through this in detail. We'll use projection operators. I don't know. We'll do it a dozen different ways. But what you will see is that the presence of the recording device over here destroys the interference. So if you actually did a measurement to determine which way the electron went, then probabilities would add as they do in classical physics. It's only if you don't record which way the electron goes, so that nobody will ever know, so that there's no record left in the system of which way the electron went, that the interference takes place. But the message for the moment, just for the moment, is that making a measurement is establishing entanglement between a device and the system. It's establishing entanglement between the device and the system. And in this case, where is it? Adding these up, adding the state vectors up, has an entanglement between whether you're at 1 and -1 and whether the electron spin or whether the spin degree of freedom is up or down. So, and the destruction of the interference is what is called the collapse of the wave function. In particular, it's the collapse of the interference part of the wave, of the probabilities, the part which has to do with the cross terms between the psi's and the phi's. They're destroyed by the measurement.
In the experiment you did before you flipped the spin to label whether it went through the top or the bottom.
Yeah.
You had a couple of entangled states there also.
What's that?
Your 2 states were entangled there also.
Before we did what?
Before you changed the experiment so that you were...
We didn't have any. All we had was this.
Okay.
Yeah.
All
right. This state was exactly the same as this state.
Okay. The state that those evolved from, just 1 plus -1.
Right. There were no ups and downs there.
Okay. You're not calling those entangled?
No. No. To have entanglement, you have to have entanglement with something. No, those aren't entangled. That's just a simple superposition of states. Simple superposition of states. Yeah, there's only one system. There's only one system, and it's the electron, and it's in a superposition of states. In the other case, there are two systems, electron and spin, and the two systems are entangled. You learn something about one of them by looking at the other. So you learn something about which orbit you went through by looking at the spin.
And then when you have it interact with that middle screen there by flipping a spin, that introduces another system or subsystem or object into it.
Yes, it introduces another subsystem into it, and it introduces a system into which the electron gets with which the electron gets entangled. Okay, it's that establishment of entanglement between system and apparatus which constitutes the measurement. Yeah.
Professor, let's imagine the same setup, and I mean it's physical. So the hole at the top has, I mean there are all sorts of atoms around there. So there's always an electron there. So couldn't an electron just, I mean, in the original case where you had interference, and an electron becomes entangled with the one that passes through. What I'm trying to do is separate the the knowledge verb and the testing verbs from the physical apparatus. Okay?
Yeah. I think what you're asking, I think if I'm not mistaken, supposing these are real things, can't this electron get entangled with an atom in the yes, the answer is it could, and if it does, it destroys the interference pattern. So that's why you cool down your apparatuses. That's why you don't want to have a lot of gas around that the electron can bump into. Photons are not so bad because photons don't interact very strongly with anything. They're much more weakly interacting than electrons. If you really do it with electrons, an electron passing through here, its electric charge might disturb something over here, and that disturbance, if this disturbance was enough, here's the criteria. If the disturbance is sufficient that when you look at the disturbance afterwards, you can tell definitely that the electron went through the upper slit, then you completely destroy the interference pattern. Now you might have a situation like this. You might have a situation where there's some degree of freedom in there, which initially had some probability distribution which looks like this. Some degree of freedom in here, position of some atom or something, and it has some quantum probability distribution that looks like this. The electron goes through here. If it shifts the probability distribution so that it's not overlapping, then when you look afterwards at the system, you know yes, no, whether it went through the upper one and the lower one. You following me? Right. Under that circumstance, that will destroy the interference pattern. But there's a less severe situation where the electron going through the upper hole here may just shift the probability distribution a little bit. And then you can't tell uniquely whether by looking at the final situation where the electron went through one hole or the other hole, then the interference pattern will not be completely destroyed.
But it is a matter of degree.
It's a matter of degree, yeah. It's a matter of how much of a disturbance and how much that disturbance tells you. Now, if you really freeze things, make them real cold and put everything into its ground state so there's nothing that is easily disturbed, then you can create pretty much the idealized situation where after you've gone through, there's just nothing that's been recorded. In particular, if the system has an energy gap, if it takes some energy to make an excitation in the system, to excite it or to disturb it, and the electron or the photon is very low energy, it may not have enough energy to make the disturbance. In that case, you have the interference pattern. So it can be a question of energetics, whether if there's an energy gap that it takes a certain minimum amount of energy to disturb the system, then a low energy photon or a low energy electron just can't disturb it, and you would have the perfect interference pattern.
So you get the interference pattern with single electrons.
Well, you can't see an interference. You can never see a probability distribution with just one electron. But what you can do is send one electron through at a time. One electron through at a time. Every 20 years you send an electron through. And after many, many electrons go through, you look at the probability distribution here. And it's the probability distribution that has the interference pattern. One electron just goes blip somewhere. There's not much you can read off that. As always, an experiment always really means either repetition of the same experiment over and over again, or many, many identical experiments performed simultaneously. But it means the recording of statistics after many events of the same kind. Right. So, to be clean about it, and we don't want to have to worry about two electrons at the same time, we send the electrons through once every 20 years and make sure that they don't talk to each other and don't give anything away to each other. And
so the effect of measurement is always to destroy interference?
Yes. Yes.
It's also destroyed.
It always has an effect of destroying interference.
It destroys the entanglement.
It destroys it. No, it creates entanglement.
No, I mean the measurement on the screen.
Yeah.
After you determine which particular element is landing at.
Yeah. Right. Right.
It destroys interference. It creates entanglement.
It's the entanglement which corresponds to the measurement itself, the formation of entanglement. But once it becomes entangled with the apparatus, we'll talk more about measurement.
Yeah, I don't think of the metal as much as the measurement. I mean, it's just the fact you're letting it interact with the metal set of slits now by magnetic field, which is changing the spin perhaps, but.
You can do another measurement over here. We could do another measurement over here, and that measurement over here would further collapse the wave function and throw away some of the entanglement. You're right. But this measurement over here is the establishment of entanglement. A second measurement could be establishment of entanglement with yet another system. If we put another electron over here. It's a question of observers, observing observers, observing observers. We could even have an electron a spin which would monitor the spin over here.
It's sort of like you went through the whole discussion of exactly when it's interacting with the metal screen.
Yeah.
And you're changing perhaps a spin, but you can do it a little bit, you can turn this thing from 0 to 1. So that means you're increasing the amount of entanglement.
Yes.
And that makes sense. Okay.
Yeah. You can turn up the interaction between the electron and the spin. So for example, if you had a very weak interaction, then most of the time that the electron went through, it would not flip the spin.
You can have coefficients in front of that 1 and
Yeah.
minus 1. You got it at the very top of that.
Yeah. You could certainly. That's right. You can. That's right. That's right. We could make up some other game, but the game that I made up is that we did a complete measurement. We did an accurate measurement that told us whether we went through the upper slit or the lower slit. Now we can talk about weaker measurements, measurements where we only get some partial knowledge, where we find out that it was more likely that it went through the upper one than the lower one.
Your wave function here on the other side will have states with down and down.
That's right. That's right. Instead of this one being up, there will be a piece with a down and another piece with an up. Right. And the one with the down might be the bigger one, in which case you mostly do have the interference. Yeah. So there are weaker and stronger measurements.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.